Good morning, my wonderful students, favored by God, awesome, wonderful people that you are. I hope that you're having a great day, and we're just going to jump right in here. Once again, you're going to be making a list of the keywords just to kind of keep everybody going and have incentive to making sure that you're following along. Also, please be aware that we have just 2 more quizzes and 1 test left for the year. Okay, a quiz on the second half of Chapter 11, a quiz on the bit of Chapter 12 that we're going to do, and then at the end of the year we have 1 test, and that test is going to cover Chapter 11 and that bit of 12 together. So it'll be a 150-point test rather than a 100-point, so it's worth 1.5 times. Okay, 150 out of 150 would be 100%, just so you've got your head around that. We'll do that on your final exam day, and I'll be sending out more information on that as the time approaches, but just so you've got your head around what the expectations are. Okay, so today, lengths, areas, and volumes of similar figures. Okay, it has to do with, again, with some proportionality. Okay. When you have certain segments that are in triangles or certain geometric figures, you can look at them as also being proportional. So for example, we talked before about altitudes and medians and angle bisectors in triangles. Well, they have the same ratio that the side lengths do. So for example, if I have these 2 similar triangles, these segments, if you remember from our other chapter, happen to be medians. Okay, these medians are proportional to the sides of these similar triangles, just like one side would be proportional, or 2 pairs of sides would be proportional on the sides of the triangles. Okay, so what we need to do is we need to set up ratios and proportions again. Now your keyword here is ratio. These are all based on ratio. The ratio of 16 to 12 is the same as the ratio of x to 9. So please write down keyword number 1 is ratio. 16 over 12 is the same as x over 9 as a proportion. If you wanted to, you could simplify this ratio first, or since you're using calculators, cross multiplying is probably, quite honestly, just much easier. You'd do 16 times 9, which is 144, equals 12x. And when you divide that out, you get x equals 12. So this number right here will turn out to be 12. It will not always match this. It just happens to this time. And just to review with you, x is the length of the median, which I just had already said. All right. Same thing works when you have these. Remember, when 2 figures are similar, this comes from way back, not just one dimension changes, but all the dimensions change. And so our sides definitely are proportional, but so are these other figures. Now, just to review, these are that go from a vertex and are perpendicular to the other side are altitudes. So I want you to write down that your keyword here, keyword number 2, is altitude. Keyword number 2 is altitude. So our altitudes are also proportional. So if we do 10 and 8, 10 goes with 8 like x goes with 3. 10 over 8 equals x over 3 as a proportion. Once again, you can cross multiply to solve. 3 times 10, 30. 8 times x, 8x. Divide by 8 and get 3.75. Now, if an answer ends exactly, you should go ahead and write the whole answer like that. Okay, so once again, keyword number 2 is altitude. And the third one that also has that same proportionality aspect to it is these, which are the angle bisectors. Okay, do try to anticipate the words, because the more you can think before I say it, the better off you are. All right, so x goes with 20, like 9 goes with 12. X goes with 20, like 9 goes with 12. It's a fraction. And once again, you can cross multiply. 9 times 20, 180 equals 12x. Divide both sides by 12. And in this case, x equals 15. So nice friendly proportions. A lot of what we're doing today is nice friendly proportions. Lengths, areas, and volumes. Areas and volumes get a little bit trickier, but for right now, let's just continue with this idea of regular plain old proportions. Our next theorem has to do with the same thing. If you've got proportions ratio for a similar triangle to a similar triangle, the sides are proportional, but also the perimeters are proportional. Okay, perimeter includes the whole entire side. So if the side lengths have a similarity ratio, the perimeter uses that same similarity ratio. Okay, so in other words, here we go with this. 3 and 5 are in those same spots, so those go together, AB and DE. They're not congruent because they're not congruent triangles, just similar. And if we're given that the perimeter of triangle ABC is 18, and where do we get that? We get that from adding up the sides. The perimeter is 18, and we need to find the perimeter here. You don't have to individually find the side lengths and add them up. You can do it as an entire perimeter problem. 3 goes with 5, like 18 goes with the perimeter of the other triangle. Once again, 3 goes with 5, like the whole perimeter of this one goes with the whole perimeter of this one. Once again, you've got your cross multiplying trick. And once you divide both sides by 3, we find out that this whole perimeter is 30. I don't have to find these at any point because that's not what the question asked. You could if you wanted to, but that's a lot more work. You can just go straight to the perimeter on that. Okay, so that helps us think about anything that is length-based. Okay, your basic rule is if it's length-based, then it is just a regular proportion going from this one goes with this one, like this one goes with this one. Okay? Now, what we also need to consider is there is something a little different going on with areas. Okay, so the ratio of the areas is equal to the square of the ratio for the corresponding sides. Notice that this is different. It's a square of the ratios. Let's think about why. Okay, the reason why that the ratio of the areas is equal to the square of the ratio is the sides. Think about it. Areas does deal with square units. Okay, it's how many squares it takes to cover it over. So area is a whole different concept. It includes 2 dimensions rather than 1. And even if it's an oddball shape, it comes out so that the ratios have to be squared in order to equal the area ratios. Your keyword here, third keyword, is square. So please write down that your third keyword is square. The ratio of the areas of similar polygons is equal to the square of the ratio of the corresponding sides. Okay. Keyword number 3, like I said, is square. Okay, so these 2 polygons are similar, and we want to do 2 things. We want to find the perimeter, and we want to find the area of this larger figure. We're given some information. We're given that the perimeter of the smaller figure is 80 centimeters. Notice that that's a linear measure, okay, because we're taking and measuring the distance around. And the area of this oddball figure is 320 square centimeters. I don't need to know any of the other sides for this. all I have to be able to do is do a calculation. Now our perimeter formula, our perimeter one is going to be based on a straight up regular plain old proportion, but our area one is going to be based on a square. So let's look at the perimeter one first. Okay, that's what we were just doing. Okay, so we're trying to find the perimeter of the larger one. So when I think about that, I have 12 goes with 18. We know we were given that the perimeter of this one was 80. So 12 goes with 18, like 80 goes with the perimeter of the larger figure. Once again, this is a cross multiplying, simple. 12p, 18 times 80 is 1,440. Divide both sides by 12 and you get the perimeter is 120 centimeters. Notice it says centimeters, not square centimeters, because that's how big it would be if you measured all the way around this figure. Okay, we don't have any other numbers to go in there, but that's what our perimeter would be. Now, area is a little bit more difficult because we have to deal with squares. So I've brought this over from our word problem that said that the area was 320 square centimeters for this figure. And I want to find the area of the larger one. I just have a subscript of L here. So we can think about the area of the smaller one compared to the area of the larger one as a ratio. Okay, so here we have area of the smaller compared to the area of the larger. Now, here it is convenient to actually reduce your similarity ratio. 12 goes with 18. 12 goes with 18. Smaller goes with larger. And if we take that similarity ratio and reduce it, we get 2/3. Divided by 6 gives us 2/3. Now remember, the formula said that it is the square of the ratios. So here is the square of the ratio. The area of this one compared to the area of this one is the square of the ratio, because we're dealing with areas rather than just sides or lengths. Okay? So the area of the smaller compared to the area of the larger is this 2/3 similarity ratio squared. And do make sure when you do your similarity ratio that you have the smaller over the larger, or however you decide to do it. You could do larger over smaller as long as you have the other side is larger over smaller, but make sure that they match. Smaller over larger, smaller over larger. Okay, so I need to go ahead and square that. 2/3 times 2/3 is 4/9. Then you can cross multiply. The 320 comes from the information that was given. I can cross multiply. 9 times 320 is 2,880, and 4 times the area of the larger one, and we divide it out and you get the area of the larger one is 720 square centimeters. So make sure that you're keeping in mind that the ones that deal with lengths, those are individual pieces, or an entire perimeter is a straight up just proportion and do that. But when you have areas, you have to remember to square the proportion for the sides. Okay? And that brings us to the idea of cubes. It brings us to the idea of volumes, which has to do with a cube. Your third key word is cube. Because remember, volumes deal with cubic units, how many cubes it would take to fill up these regions. So once again, your fourth key word is cube. And this is, so when we look at the ratio of the volumes, once again, I used S and L, smaller and larger, as my subscripts, just to keep track. It doesn't do anything. You're not multiplying it or doing anything with these. It's just for labeling purposes. So the volume of the smaller compared to the volume of the larger is the ratio of the sides to the third power. So I've got this problem here to deal with. It's got a lot of words in it, and it does deal with a percent. So let's do this. You have a box that's going to hold some cereal. And I've noticed this so many times when I go to the store. They mess around with the sizes to make it kind of appear as if you're getting the same amount, even though the numbers on the side say it's different, because they're trying to psychologically trick you into thinking you're not paying more when you are. So they actually do stuff like this. But you have a box that's going to hold a certain amount of cereal. You want to produce a similar box that will hold 3 times the volume of the cereal. By what percent should you increase each dimension? Okay, so we're thinking about we need to hold 3 times the volume. And we want to find out what happens to each of the lengths, the length, the width, and the height. I didn't mean to get that. There we go. In order to make that work. So here we have, I'm going to make a label, the volume of the original and the new volume. Now right in the description here, we want to hold 3 times the volume of cereal. We want the new one to hold 3 times as much as the original one, the old one. So that looks like this. The volume of the new one equals 3 times the volume of the old one. So here's what this looks like as a ratio. Well, why do we want it as a ratio? We want it as a ratio because we're going to have to take it back to this, where our 4th keyword is cube, by the way. But we need to be able to take it back to this and compare volumes and get the side lengths cubed. Okay, so let's go back to here. So here's my volume over volume. So that'll be one part. That'll be one side of our equation. Volume over volume, but the other side has to be a cube. Here's our cube. Wait, what's the W stand for? I just picked one of the dimensions. I picked width. But since each one of those dimensions has to be proportional to the dimension of the other one, I could have picked length, I could have picked height, but I just picked width. The width of the new one compared to the width of the original cubed has to equal Vn over V0. It has to equal this ratio. Okay, here's the formula. This would be Vn over V0, and it has to equal the ratio cubed. Here's our ratio cubed, and here's our number here. So in order to get this solved, I need to find out how many times W, the original one, gets multiplied. So I need to solve here. I need to try and get the new one, the width of the new one by itself. So to undo a cube, we need to take a cube root. So for those that don't remember how to do that, or we need to take a look, you can use your math button. Right here is cube root. Option 4 is cube root. Cube root of 3 is 1.44224,957, and a whole bunch of numbers down here. We're just going to round that to the hundredths place. Don't round it too close. Don't round it just to the 10th place, because that's not going to be precise enough to get you close enough. And even when we round it to 1.44, it's going to get us close but not exact. But here's what Wn over Wo equals: the ratio of the new one to the original one. Now in order to figure out, we want what percent. Wait a minute, what percent? We'll get to that shortly. But I want to first find out how many times the original. So we're going to multiply both sides by the original. So this gives me my new one is 1.44 times the old one. The new width is 1.44 times the old width. If we had had length, we'd have the new length is 1.44 times the old length. Or we could have the height is 1.44 times the old height. It would work out to be the same math each time. But you're asking for percent. Yes, I am. Okay. The new dimensions are 1.44 times as great. So 100% would be the same. Okay. If you have a certain amount of anything and you are allowed to keep 100% of it, that means that you've kept it all and you have the same amount. Okay, we're not talking a percent of increase. We're saying how much of it do you have. But if you have an 100%, remember, is 100 over 100, which is just 1. So when we have 1.44 times as much, it means that this 0.44 part, that's our increase, that's our percentage up. So we can ignore this 1 and say that it went 44% bigger in each dimension. Okay, I bring this up because we have to look at some difficult questions sometimes. When you take the SAT to help qualify you for certain colleges and scholarships, there might be the harder questions. I don't want to neglect them. Sometimes some of the questions on your tests are very, very challenging, but some of them are way easier. But then when you get to the SAT tests, they throw things at you that are curveballs, and the more you can practice the more difficult things, the stronger you will be for those type of tests. Okay, so this is a more difficult one. Remember, the volumes are based on cubes, and you could have a problem like this. All right, with this I'm going to end my lesson for today, and you're going to work on assignment 62, which is due the beginning of the period tomorrow. It's just like in school. You would have a lesson, and then you would go home and work on the homework, and then you would turn it in the next day. That's the way I'm handling it. So go and work on your assignment, and have a blessed day.